Okay, thank you. Good morning, everybody, also from my side. So before I start into the scientific part of this presentation, I would like to thank a few people. First of all, of course, the organizers for setting up this program and for giving me the opportunity to speak here. Second, the Academy of Finland, which is generously funding my research, and the Center of Quantum Engineering for all sort of non-financial support. And finally, of course, also my collaborators in this work, who have been Christian Flint, my supervisor, Juan Garahan, who will also be here next week on the theory side. And the experiment I will talk about has been carried out by Ville Maisi in the group of Jukka Pekkola. Okay, so here's the outline of the talk to let you know where we are going. And I will essentially proceed in 3 steps. So first I will explain some generalities about the concept of Young zeros for all those who are not yet familiar with it. In the second part, I will establish a connection between Young zeros and dynamical phase transitions. And finally, I will try to convince you that all of this has something to do with large deviation theory. Okay, so here we start. So Young zeros are actually a pretty old concept. It was introduced in the 1950s to explain some properties of maybe the most prominent example for thermodynamic phase transition, and that's the condensation of a gas into a liquid. So here's how the principal idea works. So the system is the following. We have a gas confined in a very large container. So the volume is infinite for all practical purpose. And this container is in contact with a thermochemical reservoir, which has chemical potential mu and a temperature T. Now what I'm plotting here is the density of particles inside the container as a function of this dimensionless parameter theta. And what you see is, of course, as we increase theta, that means we cool the system, essentially we decrease the temperature, the density increases slightly until we reach a certain critical value, then we observe a jump in the density. That's the point where the transition to a liquid happens, and then the density continues to increase in a smooth way. So that's, of course, the phenomenology of this phenomenon. How is that explained now in statistical physics? Well, everything starts with a Hamiltonian, as always. Here we have interacting gas particles, a kinetic term, and some interaction energy. And then we have a grand canonical partition function for this system, which essentially looks like this. So this is a classical system. Indistinguishability of particles is taken into account by this 1 over n factorial factor. And here we have an integral over the n particle phase space. So this part is essentially the canonical partition function given here for a fixed number of particles and a fixed volume. And the grand canonical partition function is then as the discrete Laplace transform of this object. Okay, so far so good. Having this object, I can introduce a thermodynamic potential, which by slight abuse of terminology I will call the free energy here, and that's just the log of the partition function. Now, this parameterization of the problem has the advantage that I can now write the average number of particles in a container directly as the first derivative of f with respect to theta, and all the prefactors have been eliminated here. Okay, now what do we see here? We have at the critical value of theta a jump in the density. This jump must come from a jump in the discontinuity in the average particle number, since we keep the volume constant. The average particle number is the first derivative of the free energy, so we can conclude at this point the free energy is a non-analytic function at the critical value of theta. Okay, so that's the system. Now, what is the idea of Young zeros? Here we go. So we start now with a finite system, which means I keep the volume at some finite value. Then I can truncate the partition sum at some maximum value of n, because only a finite number of particles can be clamped into a finite volume due to repulsive interaction. So this object now with respect to theta is just the sum of exponentials, which is of course an analytic function. And for an analytic function, I have a product expansion which essentially looks like this. So nu and chi are some constants here, which are irrelevant from here onwards. And the objects Cj and Cj star, which denotes the complex conjugate, are the Liang zeros. So these are basically the complex values of theta at which the grand canonical partition function vanishes. Okay, so what do we know about the location of these Liang zeros in the complex plane? First of all, they cannot be on the real axis because the partition function can trivially not be zero for any real value of theta. And second, we also know that these Liang zeros must have a finite distance to the real axis. So what you see in this plot is the leading Liang zero. So from here onwards, C0 will be the Liang zero which is closest to the real axis. And this object I will call the leading Liang zero. And the free energy, which is the log of the partition function, and therefore has logarithmic singularities at the Liang zeros, is analytic within this area indicated here by the blue circle. Okay, so what does that show us? As long as the system is finite, the Liang zeros are offset from the real axis, so we have a finite range where the free energy is analytic. Consequently, we cannot observe a sharp phase transition in the finite system, but we have a smeared out transition which somehow looks like that. Okay, so far so good. Now we increase the volume, of course. And what happens is, and this is quite generic behavior, the leading Liang zero starts to move closer to the real axis as the volume of the system becomes larger. Please make sure what you see here is the trajectory of the leading Liang zero as a function of the volume. Of course, there are many more zeros out there, in particular in the limit where the volume goes to infinity, there are infinitely many, but here we only care about the leading one, so the one which is closest to the real axis, because this leading Liang zero determines the size of this area where the free energy is an analytic function. And what you see here very nicely is as the leading Liang zero closes into the real axis, this area becomes smaller and smaller. Simultaneously, this transition becomes sharper and sharper, and in the limit where v goes to infinity, we come arbitrarily close to the real axis here, and we develop this discontinuity. Okay, so that's the basic idea. It's very, this is a very simple argument that can be made mathematically a bit more sound, but for the present purpose, I hope that's okay. Yeah. So now, let me show you how these objects are related to fluctuations. A very characteristic property of phase transitions is that the fluctuations diverge at the critical point. And that's also what we observe here. And the physical picture behind that is somehow illustrated here. We start with a gas. And as we decrease theta, so as we increase theta, so as we decrease the temperature and come closer to the phase transition, there start clusters to develop where the system is actually already in the liquid phase, and these clusters are immersed in the gas phase somehow. That means that the fluctuations, the density fluctuations, become very, very large at the critical point. Sorry? This is first. Why not? The particle number fluctuation is the second derivative of the free energy that diverges. Yeah. Yeah. No, that's not a region. Okay, but they blow up at the, you can see that easily here. If you take the derivative of this function, yeah, you get something which looks like a smeared delta. And that's also what you observe here. Yeah, okay, so, but you're right, of course. You have this divergence at a single point, it's not a region. Anyway, the physical picture is that you form clusters of liquids inside the gas phase. And by the way, as a side remark, since we are talking about that, this is also the reason why this whole idea was introduced, namely to explain why the Mayer cluster expansion does not converge beyond this phase transition. So the idea behind the Mayer cluster expansion, which is very old, it comes from the 1920s, is to expand the partition function in a non-trivial way, essentially in the density of the gas. And what happens there is you take clusters of particles, yeah? And this converges very nicely if you go from the gas phase and you indeed see the transition from a gas to the liquid. But then beyond this gas-liquid transition, the results of this expansion become physically implausible and it does not converge anymore. And that's also, I mean, that was the original motivation in the 1950s for Lee and Young to introduce this concept. And the reason why this expansion does not converge is because you have the series of singularities here. Yeah? So if I start from somewhere here, I can never get converged there. That is the idea. So that's where it comes from. Okay, now how can we exploit that? So first we quantify the fluctuations in the particle number with high-order cumulants, and that's just high-order derivatives of the free energy. Yeah? That's exactly what I was saying. If I take the second derivative, I get the fluctuation number, and then of course I can continue to higher order derivatives as much as I want. And now I use the product expansion for my partition function, and I get exactly this expression here. Here, theta naught is the value of my control parameter at which I evaluate these fluctuations. So I'm sitting somewhere here at the value of theta, which is below the critical value, and I'm now evaluating the higher order fluctuations. And you could technically imagine that I'm measuring the particle number in the system and in this way experimentally determine the fluctuations. Okay, now the crucial approximation is the following. I assume that this n is relatively large, so the order of the cumulant I'm looking at. And then I can basically throw away all but the first contribution in the sum. So the first contribution is the Liang zero, which is closest to my expansion point, and I assume that this is also the Liang zero, which is closest to the real axis. All the other ones are further away, so higher order contributions in the series are suppressed as the ratio of this distance to the n, small n. Yeah, if you want to classify the order of the phase transition. I mean, the thing is that at this point, the system is still finite. I'm looking actually at a very small system here. Imagine I have 30 particles. Then I have only a relatively sparse pattern of zeros in the complex plane, and the concept of a density doesn't really make sense. The concept of the density makes sense in the thermodynamic limit, where I get a continuous pattern of Liang zeros. And then, indeed, you're right. If you, for example, want to classify the order of your phase transition, you have to look at the density. But all I want to do here is, in the end, I want to figure out where the phase transition happens. And to this end, I only have to know at which point my Liang zeros close into the real axis. Okay, and now, okay, the thing is, I performed this approximation here, and I assume it's good within a certain range of parameters. And this range of parameters is defined in a pretty subtle way because my system is actually not allowed to be too large at this point. Because what happens, and that's exactly what you were saying, as I make the system larger, these Liang zeros accumulate to a continuous pattern, and then the difference in the distance to my expansion point becomes very small between the leading Liang zero and the next one. And then this approximation is not good anymore. So I assume I have a relatively small system. Okay, but once I have done that, so please believe me, it's okay at this point, I can easily invert this formula, and what you get is this, with the objects eta defined as ratios of successive cumulants. And that tells you if I know 4 successive cumulants of sufficiently high order in a sufficiently small system, I can calculate the polar coordinates rho and phi of the leading Liang zero with respect to my expansion point. Okay, so I have a connection now between the leading Young zero, or the coordinates of the leading Young zero, and the higher order fluctuations of my system. Okay, so that's the take-away message here. Now, before I want to tell you what that has to do with dynamical phase transitions, let me briefly switch gears and explain a little bit the experiment for which we were doing that. So the setup is what you see here. You have two superconductors. These are gray area here at the side. And in the middle, you have a normal conducting island. Everything is at very low temperatures. And it's also very small, so this is 1 micron. Now, what happens in this setup is schematically illustrated here. In the superconductor, you have an energetic gap. In the normal conducting island, you have just normal Fermi-Dirac statistics, or normal Fermi-Dirac distribution. And now we are interested essentially in the following processes. I assume that the island is so small that I can basically have only a single charge on the island. That's a very good approximation because of Coulomb blocking. Yeah? So I can either have a particle an electron on the island, or a hole, or the island can be neutral. But all higher charge occupations are energetically so unfavorable that we can neglect them. Now what happens is, if I have a hole, for example, I can absorb a Cooper pair from the superconductor and directly switch to an electron. Or if I have an electron, I can emit a Cooper pair into the superconductor and end up with a hole. So I have a direct transition between electrons and holes. That's called Andreev scattering. And besides that, I have, of course, thermally induced transitions because everything is still on a thermal substrate. Yeah? So I can emit an electron from the island also somewhere into the environment, and I can also absorb an electron from the environment. But the interesting processes we are after are these Andreev events. Okay. So how do we describe that? Here's again a scheme of the setup. We have the normal conducting island with the superconductors. They are separated by insulating barriers. And this is the state diagram. It's very simple. This is the zero charge state. Then we have some rates. These are the thermal activation rates, which describe the absorption or emission of a single electron. And this is our Andreev tunneling, which comes with the rate gamma A. Gamma D and gamma U, of course, satisfy a detailed balance condition here. Gamma A is the same in both directions since the charge states are energetically degenerate. So how do we measure that? We measure that in the following way. Here is a so-called single electron transistor, which allows us to monitor the charge state of the island. Basically, via detector current. So what you see here is the detector current plotted as a function of time. This is real experimental data. And whenever this detector current is within certain margins indicated here by the dashed lines, we know we are in the neutral state. As soon as it fluctuates above a certain threshold, we have a single electron on the island. And as soon as we go below, we have a single hole. And now you see events like this one here, where you fluctuate up and you have a single electron, and then you go back to the neutral state. That's a single particle event. So here we have just absorbed an electron from the environment and thermally emitted it back to where it came from. But the interesting events are shown here, shaded in blue. So these are these direct transitions between positive or negative positive charge states, and these indicate Andreev events. So if we just count these transitions here, we can count the Andreev events. So mathematically, we do that in the following way. We introduce a moment-generating function. I guess this object looks familiar to everyone. And it can be seen somehow as a dynamical ensemble of trajectories. Yeah? And now here P of k and t is the probability that at the time t I have observed k Andreev events, S is my counting field. Yeah, that's basically it. And associated with this moment-generating function, I have a cumulant-generating function, which is just a log. Now, how is that connected to Young zeros or thermodynamic ensembles? So this is the analogy which I trying to build. In the thermodynamic ensemble, for the gas-liquid transition, we had an expression like this for the grand canonical partition function, and now we have something like this for the moment-generating function describing our Andreev tunneling. And I hope the formal analogy here is obvious. So, of course, S or minus S, the counting field, now plays the role of the control parameter, and the extensive quantity K, which is the number of jumps on my trajectory, plays the role of the particle number here. And then the free energy is replaced with the cumulant generating function. And now by sheer analogy, I can define the concept of a dynamical phase transition at the process, or I can, as a process where the cumulant generating function becomes non-analytic at long times, in the region where I have many, many jumps, as a function of the counting field. So this is the idea, and here's the graphical analogy. When my counting field is very large, I'm exponentially suppressing all trajectories with many jumps. So I virtually drive the system into a phase where nothing happens. And if the counting field is very small, I have a region in my dynamical ensemble where I have basically only these highly fluctuating trajectories between the both charge states. So I have a lot of Andreev effects. So the left one, this one is the active phase, and this is the inactive phase. And generally, the crossover will be smeared out, but as we increase the time, it can technically become sharper and sharper. And if it becomes an abrupt jump at this point, we say that we have a dynamical phase transition. So that's the idea. I'm basically introducing the concept of a dynamical phase transition here by formal analogy with a thermodynamic phase transition. Okay, now, I mean, since I have this beautiful formal analogy, it's clear that I can also build my Young zero formalism for that. It works exactly in the same way. I start with the moment-generating function at some finite time. Now I can assume that this sum is finite because the probability to have a very large amount of jumps on the trajectory in finite time is exponentially suppressed. Then I have an analytic function in S. I can do the product expansion. These objects are my dynamical Young zeros. And again, we will be looking only at the leading Young zero, so the one which is closest to the real axis. Okay, now I can do the same trick again with the higher order cumulants. So I define higher order cumulants as the higher order derivatives of the cumulant generating function, evaluated now at s equal to 0. That's the crucial point here. Before, I was evaluating this cumulants essentially at an arbitrary value of the control parameter. Here I have to do it, of course, at s equal to 0, because we have to keep in mind that s is still a fictitious parameter. I mean, this is the counting field, that is not a physical parameter which I can tune in the experiment. But at s equal to 0, basically all the physics happens. So if I evaluate this object at s equal to 0, these are the real cumulants which I observe in the experiment and which I can use then for further analysis. Okay, now then playing the same game as before, I get this relation between the leading Young zero and ratios of high order cumulants. This is exactly the same as we had before. This formula now gives us an opportunity to indirectly observe a dynamical phase transition, even if it happens at the complex plane, so in the complex counting field plane. Because what we can just do is we can take these cumulants, those we can calculate from the experimental data, plug them into this expression, we get the coordinates of the leading Young zero, then we do that time resolved, we see this trajectory, and as the trajectory closes in or converges to some point, we can identify dynamical phase transition. So that's the strategy. And that's exactly what we're doing. So we start with the stochastic trajectories, which we get from the measurement. Then we evaluate the high order cumulants. High order here means, for all practical purpose, that we look at cumulants n equal to 4 and n equal to 7. That is enough. I mean, we checked that if you go to higher orders, nothing changes. So this is enough within within the accuracy of the experiment. And now what you see is you get exactly what you expect. This is the leading Young zero here as a function of time for 35. Yeah. No, I mean this is a log scale and they keep growing. They grow, I think, factorially, asymptotically. Yeah, they grow with n factorial. With time. How do they grow with time? Well, they become linear in time. They become linear in time. Because your moment generating function, I will talk about that in a minute, satisfies the large deviation principle. And then this is basically just the higher order derivatives of the large deviation function times. Okay, but anyway, we take the cumulants, which we get directly from the trajectory, then we evaluate the leading Young zeros, and what you see here is the trajectory of the leading Young zero in the complex plane. Of course, they come in conjugate pairs, because our moment generating function is still a real function. Yeah, so this is the trajectory for 35 milliseconds, and these red dots indicate the convergence points. So if I would continue doing that for very long times, I would eventually reach these red dots. How do we determine these red dots? Well, very simple. We plot the real and imaginary part of the leading Young zero separately as a function of 1 over t. And what we get is, after some transient behavior here, we run into a very nice linear regime for both the real and the imaginary part, and then we do a linear fit in this regime, and we just extrapolate to 1 over t equal to 0, which means t to infinity, and from this procedure we get the real and the imaginary part of the convergence point. Yeah? Yeah. I mean, all sorts of things can happen here. I mean, this is not mathematically completely understood. I mean, I have not a mathematical rigorous proof that the scaling of the real and imaginary part is really 1 over t in a large t limit. But it looks like that, and I'm a physicist, I'm allowed to assume it's okay if it looks like that.
No, but I mean, my point is, if you don't have analytic control on that, this kind of estimation might be really dangerous.
Yeah, it could be. But in this case, it works. I will show you. But I mean, of course, there are all sorts of subtleties. I mean, it is an assumption that we have linear convergence in 1 over t. It turns out to be a good assumption here. It doesn't have to be in another system. It's absolutely true. Okay, but anyway, what we get is from our experimental data, after we've done all that, this is the complex transition point. It's just a complex number, which we have now. But what can we do with this complex number? Also observe here that the dynamical phase transition happens at the point which is offset from the real axis. So we're not reaching the real axis. We are still staying in the complex plane, which means that we have a smeared out transition. I will explain it now. Essentially this is exactly what I want to do in the very last part of this talk. I want to explain what it means to have a phase transition at the complex plane and what we can do with this information that we know a complex transition point and what all of this has to do with large deviation statistics. Okay, so now we do the following, which I think is basically a standard analysis. We now make a model for our system, which essentially looks like this. This is a coarse-grained model. So what we want to calculate in the end is the moment generating function. The moment generating function can be written in this way. Here P0 is the stationary state of the system. This vector just contains the number 1. And the W of S is the object which was called the tilted generator before. And it looks like this in the coarse-grained picture. It's just a 2 by 2 matrix. These up and down tunneling rates are just the thermal transition rates between the zero charge state and the single electron or single hole state. And these objects here are the generators, or the moment generating function, if you want, of the individual phases. This is a coarse-grained picture. Yeah? We assume here that we have some timescale separation. So the jumps within these avalanches of Andreev events happen much, much faster than the jumps between inactive and active phases. The inactive phase is actually trivial because nothing happens there. So this object is exactly equal to 1. And the active phase is more interesting. That's the part of the part where we have the Andreev events. If I wanted to determine this object exactly, what I would have to do is I cut out only the shaded parts of this trajectory, so only the parts where I have Andreev events, and then do the full counting statistics only of these Andreev events. But this happens very fast compared to the timescales we are interested in, and that means we can do the following approximation here. We throw away all fluctuations in the individual phases, and we just approximate this generator by its lowest order in the counting field. And this current J alpha can be determined with very high accuracy. Okay, now I guess the next steps are pretty obvious. So as we discussed before, the moment generating function satisfies a large deviation principle. So we have this large deviation function psi of s, which depends on the counting field. If s is real, this is a very nice behaved convex function. So I can do the Legendre transform, and then I get the large deviation function for the current phi of j. Okay, now I can calculate everything explicitly because this is only a 2x2 matrix. And then I get this expression for the large deviation function of the current. And as you will see on the next slide, this is just the mathematical description of a tilted ellipse. Now the crucial point is here, in this expression, I have the mean currents in my individual phases. The inactive current is, of course, trivially 0. And the active current is just the average number of Andreev events per time, given that I am in the active phase. Yeah? So I'm basically collecting all these shaded areas, and then I'm just doing the average over time. That's how I get this active current. And all the rest in this ellipse now just contains the real part and the absolute value of my complex transition point. So I can express the large deviation function in terms of the transition point, which lies somewhere out in the complex plane. Now, this is now a real object, which has, of course, a real physical meaning. And it looks like this. Okay, so this is the tilted ellipse. There's only the upper part that could be closed, but the large deviation function is, of course, only this upper part. It has a certain tilt, and the tilt is determined by the real point. And the tilt essentially tells you in which phase you are. Yeah? So if the ellipse is tilted like this, we are strongly biased towards the inactive phase. If it would be tilted in the other direction, we are biased towards the active phase. And then this object has a certain width. And this width is essentially determined by the imaginary part. Now that makes good sense. If you observe the following, since we have a finite imaginary part in the transition point, the transition is smeared out. Yeah? So we have, in reality, something, if I would plot my activity as a function of the counting field, it would look somehow like this. Yeah? So I have a smeared crossover. But if the imaginary part of my transition point would be very, very small, this would become sharper and sharper. And that would mean that the width of this ellipse would become smaller and smaller. And in the limit where I'm actually closing into the real axis, this becomes just a straight line. And then you see what happens is, as long as the straight line is tilted in this way, I have the maximum probability here. So my mean value lives here. Then I continue tilting that. At the phase transition point, it will be a vertical line. That's exactly the point where the fluctuations blow up. And then if I go beyond the transition point, my mean value will suddenly jump to somewhere here. this is just by rotating the straight line, I get an abrupt jump in the mean value of the activity, and that would be first order phase transition. You could have exactly the same picture for a thermodynamic system. But since I have a finite width of the ellipse, this transition is smeared out and in fact happens continuously. Okay. Now, what you see in blue is the comparison with the experimental data, and that's one of the crucial points here. This entire ellipse has been obtained from measurement data for 35 milliseconds. So we needed 35 milliseconds to get the complex transition points, given, of course, that we buy the linear extrapolation. And then there is no fitting parameter here anymore. There is, I admit there is a trivial offset, which we're adjusting, but besides that, there is no fitting parameter. So we do this analysis at 35 milliseconds, and we get this entire ellipse. What you see here in this small box, which is plotted here a bit larger, is the maximum measurement data we have for 3 seconds. So this is the longest trajectory we have. And what you see is it fits actually very nicely. So we have a very good agreement with the, let's say, intermediate time data with the large deviation function, which we have inferred from very short measurements. And moreover, we now have the large deviation function also in regions down here, which would not possibly be accessible directly in the experiment. So that's the main takeaway message, I think, of this whole talk, that by going through this entire procedure with high order cumulants, Young zeros, and extrapolation, you can get the long-term statistics of the systems from short-term measurements. And also, I mean, these mean values here, these currents, this is something you can access in short-term measurements, yeah? Because you only have to look at the active phase. The inactive phase is trivial, and you only have to look at the active phase. There, the Andreev events are fast. They happen at the rate of about 600 hertz. So this mean current, and you only need the mean value, this you get very easy at short times. Okay. Yeah. I mean, 600 hertz is the average rate of Andreev events you have in the active phase. So if I would keep the system in this active phase where I'm jumping between these excited states all the time, I would get the 600 hertz. But in reality, I'm fluctuating up and down. So if I can go back. Yeah. So in reality, I have fluctuations between active and inactive phase. And now, of course, if I look at the average over the entire trajectory, it will be much smaller than 600 hertz. You can tune the rates. You can tune. I mean, actually, this experiment is, of course, much more complicated than what I explained. You have all sort of gate voltages and stuff. First, to stabilize it. Second, you can also tune the rates within certain margins, of course. Yes, please. Oh, yeah, you can. But this is what we throw away in the analysis. So in reality, you would have a smeared out tail somewhere here. So it would not be a sharp cutoff. There would be some smearing out. But this is what we throw away at this point. We approximate the generator of the individual phase by the mean current, which basically means we throw away the fluctuations in the individual phases. But they would be there in reality. It's only that we are here not looking at it. Essentially, what we get from this analysis is the switching behavior between active and inactive. And the individual events are all, I mean, the statistics of the individual Andreev events is not resolved here. That's all buried in this value, J alpha. Okay, I have 40 seconds left. That should be enough to give the summary. So what I was trying to convince you is that we can take a short-time trajectory of a stochastic system, calculate high-order cumulants. From those, we can indirectly infer the trajectory of leading Young zeros as a function of time. By doing some extrapolation, we get a complex transition point. Using this complex transition point, we end up with an expression for the large deviation function. Thank you very much. I'm always inclined to join clapping. And I hear other people clapping.
Any questions?
Is this procedure different than just calculating the cumulants and then resumming them? Is there a fundamental difference between doing that and what you're doing?
What do you mean? I mean,
You measure the cumulants and
yeah.
you just resum them to get the generating function in some approximation. And I'm just wondering if what you're doing is different than that.
So what you're saying is by measuring the cumulants, I have the Taylor expansion of the cumulant generating function to a certain order. I think it is different because if I have a finite truncation of the cumulant generating function, I could technically do the Legendre transformation, but that would not give me the ellipse. So the ellipse is an object. No, I'm doing more. The ellipse is an object which emerges in the long time limit. So in the limit where technically all orders of my, well, probably all orders of the cumulant generating function would contribute. I'm doing an extrapolation at some point, and that's where I'm implicitly going to infinite time. The ellipse, okay, if that's the question, the ellipse follows from the fact that we have square root branch points. So that's what you were saying before. If I go to very long times or very large system size, then my Lie zeros develop into some continuous whatever kind of singularity. In this case, it's a branch cut. It's a square root branch cut. And what you can show relatively easy is whenever you have a square root branch cut, then you get this ellipse. And here you have it, of course, trivially, because you have a 2x2 system, and the phase transition happens where the eigenvalues of this matrix cross, yeah? And since it's 2x2, this is, of course, a square root branch cut singularity. In this sense, it depends on the underlying system, yes. But it does not necessarily have to be this 2x2 system. Yeah? I mean, it could be larger, and then you have the phase transition when the two leading eigenvalues cross, and then you would still have a square root branch cut, and you would still get the ellipse.
But the data doesn't specify the ellipse. The ellipse is coming from the model itself, and then you can only say that the data is consistent with the ellipse, but to say that the data determines the ellipse is a bit of a conclusion, no? What I'm probing is one part of the ellipse.
Well, I mean, of course, there's an underlying model. I mean, it doesn't work without having any idea about the system.
But I could use the data only to plot the rate function like you do, and then you get that region there.
I could do that. I could do that. Okay, sorry, I'm going in the wrong direction. What you mean is basically, I could take the 3 second, yeah, then I would have this, but I would know nothing more about it. Would be a bit boring, no?
Yeah, but can you go beyond the data, really, to say that you're determining the ellipse?
I mean, I have the ellipse out down here in a region where I have no data, and where I would never get data in a finite time.
Yeah, but I think his point is that given the data that you are available, the rest could go model.
The rest is determined by the model that says that you should have an ellipse, and then from the ellipse you only have to fit the complex zeros. But if I didn't have the model, I couldn't make that connection.
No, but I mean, if you think about the model, it's not so specific. Essentially, I'm assuming that I have Markovian dynamics. That's basically it. Or what else do you think goes in there? I mean, I have two phases, but this is obvious, no? No, but these states are phases, yeah? This is a coarse-grained picture.
But also, for instance, what Grant was mentioning is the fact that you have an upper bound on the activity is also an artifact of the ellipse. It's an artifact of the model.
Yes, sure. It's an art. I mean, but it is physically clear where it comes from. It comes from the fact that I'm throwing away these fluctuations. I mean, of course, there is an underlying model. I'm not saying that basically I take only the data, do some magic, and I get the ellipse. I'm making a model of the system. Yeah. And essentially what goes into this model is that I have Markovian dynamics also on the coarse-grained level. So I assume that I have also Markovian switching. But this model still comes with a lot of free parameters. Yeah, I have all these rates. Now, if you want to determine the switching rate, for example, between these active and inactive phases, you would never be able to do that in a decent accuracy in 35 milliseconds. So you would have to have a very long trajectory. I mean, here you have it, but technically, I mean, here we have the advantage that we have 3-second data. But technically, we would have only 35 milliseconds, and then you would basically see these few dots and nothing else. And still, we would have the full ellipse. So there, I mean, there is an underlying model. There are some assumptions, of course. Not all of them can be made mathematically sound, at this point at least. But still, there is also some benefit in it.
Within these settings, how would you distinguish a model or a system which has a dynamical phase transition from a system which has no such transitions?
Well, I mean, if you have, I mean, now it depends on what you call a dynamical phase transition, yeah? I mean, technically you have one, it's only in the complex plane. If the question is, when does it happen on the real axis? Well, that's relatively easy to observe, because you get the transition point directly from the analysis, yeah? And you would also see that, by the way, there is a paper by, I have it somewhere. Yeah, here. Juan can maybe tell you more about that also. Here in this paper, they basically do a similar analysis for numerical simulation of glass-forming systems. And there they have the phase transition exactly at s equal to 0. So you would have them in real life, I mean, in real physical space. So that's possible. And then what you see is that your Liang zeros just converge to s equal to 0, so just to the origin. Does that answer the question? Or? I'm very happy to explain more later if you want.
If you go to the scaling of the Yang-Lee zero, so the experimental one.
Yeah.
So we know that the order of the phase transition is the angle at which you're pinching the axis.
Not only, but yes.
Yes, but so like first order you pinch with the line, and then second order you actually pinch with the 90-degree angle. But here from the data, can I not say from the left?
I think first order is 90 degrees.
No, but suppose I pitch the real axis, and then the angle at which I'm pinching determines the phase transition. If
Also, and the density.
With like a curvature, then I have second order, don't I?
It's both. It's the density and the angle, if I may say that. If you hit the real axis at 90 degrees, I believe that's first order, if you have a homogeneous density of your Liang zeros close to the transition point.
But here, do you see that it crosses at 90 degrees? I don't
No,
see this.
but there's also no phase transition on the real axis. But I mean, you can easily imagine that if these points would be, I mean, what you could do is you could technically think about tuning the system into a region where these points move closer to the real axis. That means reducing the up-tunneling rate, essentially, the system. Then these convergence points close in. And then you could easily imagine you have a trajectory like this, yeah? It could go like this. I mean, you could have 90-degree approach here. I mean, it doesn't have to, I mean, the fact that you have a first-order phase transition doesn't have to mean that all your Liang zeros lie on a straight line. That's typically not the case.
It's just the local pinching.
Exactly, the local pinching, but the local pinching can still be 90 degrees. I mean, that's simply not, to be honest, it's not clear from this data. But if you, I mean, what you can do is you can do the numerics, and I actually did that for the system. I mean, it's not so difficult, and then you would see it.
Yeah, but again, you'd be using the model to interpret the data.
Yeah, but I mean, I'm doing the numerics here as a double check. I mean, I have never used that in this analysis. And it's clear that it should be a first-order phase transition, I think.
From the data, it's not clear.
From the data, it's not clear, but from the physics behind it.
Again, okay.
Physical intuition is a valid argument.
Yeah, of course, you can play between the model and the data, but suppose I wanted to do like an observation only with the data and then try to conclude something with the data. From the data, it's not so conclusive.
No, it's not a black box if you're saying that. No, that's not the case.
Yes.
Can you also do the same analysis for the current fluctuations instead of the counting field fluctuations?
I mean, not sure if I understand you correctly, but
because here you count in the same way the arrival and the departure of Cooper pairs in the system, no? So
yes.
Subtract.
You mean I could only count one direction?
Or one minus the other. So actually measuring the current flow in the system.
I could, in principle, do that. I guess it wouldn't change the qualitative results. For the moment, I would guess so. I mean, in principle, one could do it. I have done it, and it shouldn't change so much, right?
Other questions?
How feasible it is to, instead of do the single particle problem, connect many of these in a row, many normal regions.
Okay, so I mean,
Do more thermodynamic.
yeah, okay. I guess the question somehow aims at how is it possible to tune the system into a real phase transition, which would mean I would need infinitely many copies. In the experiment, no. So it was complicated enough to make this setup and also to maintain it stable. You could maybe do 2, maybe 3, but I don't think you can go beyond single digit.
Other questions? If not, let's thank Kay again.